Okay, I'm going to start taking a look at some of the questions in the review packet. I'm not going to do all of them. We have solutions that are published in D2L. So I'm going to pick a few from each section and do them, and then maybe have some general comments about the exam. So these are from one of the two review packets. Let me see which one this is on. I think this is the one, like the exam 3, yeah, the chapter 6 review here. So first, some problems about indefinite integrals. Let's do these ones quickly here. Actually, originally this problem right here was written as a square root minus x to the 1/2 power. Anytime you have roots, it doesn't matter whether you're doing differentiation or integration, we're always going to rewrite that in terms of fractional powers. And I want to be, I'll be candid about something that I've seen here. I've seen some people do the following. So we have the integral of the square root of x, and then they just write this. It's x root x plus c. This is true, but this is 100% what a computer or solver will tell you to do, and not how real people actually work a problem. When we integrate, we first rewrite it as x to the 1/2 power, right? And then when we integrate, we increase that by 1, so we end up with x to the 3/2, and we multiply by, sorry, there's a 2/3 in here, I forgot that too. Then we multiply by the reciprocal, which is 2/3. Okay, so up top, this is how a computer does it. This is how a human does it. No one in their mind increases this to the 3/2 power and then writes it as x root x. It is x root x and x to the 3/2 power are the same, but it's just like a really clear indication in almost all cases that someone's work was based off of an outside source. So please make sure you're doing your own work, and please make sure you show all your steps. So I'm going to do this problem here. So I'm going to increase the power of x by 1 in each one of these terms here. So that will give me x to the 4/3, right? 1/3 plus 1 is 4/3. And so we'll multiply by the reciprocal of 4/3, which is 3/4. And then like I just did, we're going to increase the power of x to 3/2 here, and multiply by 2/3, and finally increase the power of x from x to the 0th to x to the 1st, and then the last part is plus c. In any indefinite integral, make sure you put that plus c. You won't get full credit if you don't put that plus c there. Okay, so problem 2. And remember, for problem 2, we can always do algebra before we do calculus, and this is a good example of a spot where we really need to. We don't have a product rule for integrals here. It's not going to be the antiderivative of the first times the antiderivative of the second. And we know that because if we were to check our answer by differentiating, that would not work, right? We'd have to use the product rule of derivatives to go backwards there. So first thing I'm going to do in this problem is actually use FOIL to multiply this out. And so my first term will be x squared times x to the 1/2, so that's x to the 2.5. So x to the 5/2. I still haven't taken any antiderivatives. I'm just expanding this here. And then we'll have 1 times root x, so x to the 1/2. And then we'll have a minus x squared, so that term. And then finally our last term is minus 1. And all that's times dx. And so now we can just go term by term as we would normally do, and obtain x to the 7/2, right? That's what happens when we add 1 here, times 2/7. Plus, well, we just did this about 3 different times, so we can just write a result from before, 2/3 x to the 3/2, minus x cubed over 3, minus x, and plus c. And we're done with that problem. Let's make a little line here so we don't get confused about the work. Okay, so third example here. I have a rational function, x minus 1 on top, x squared minus 2x plus 5 on the bottom. I'll mention, you are allowed to, if you're able to simplify this, you're allowed to do that. Unfortunately, x minus 1 doesn't go into x squared minus 2x plus 5, at least not evenly. And so this problem is a good candidate for u substitution. So some suggestions on u substitution. Almost any rational function that we're going to integrate will need a substitution to do so. And there's this question of what our choice for u is. Two clues. One clue, if we have two polynomials that differ in degree by 1, we're going to take the higher degree polynomial. So we're going to take that x squared minus 2x plus 5 as our u and see what happens from there. So let's do that. So let's let u equal x squared minus 2x plus 5. By the way, there's also a hint. If you have a rational function like this, first look at the degree of the numerator and the denominator. They'll almost always differ by 1, and you just pick the higher one. It's also true that oftentimes in a rational function, the denominator ends up being your choice for u. But that's a little bit less of a strong pattern than the degree of the polynomial. So if we let u equal x squared minus 2x plus 5, that means that du dx is 2x minus 2. Or equivalently, du is 2x minus 2 times dx. Okay, so let's see what we have here. So then we would have a u in the denominator. We have an x minus 1 in the numerator. I'm going to show this trick that I used before, where I change the original problem. I don't really change it, but I rewrite it in a new way. I really wish I had a 2x minus 2 dx, but I have an x minus 1 dx. If I were to take x minus 1 and multiply it by 2, right? So if I multiplied that by 2, I would get 2x minus 2. I can't just change the problem. I can't just like multiply it by 2, but I can if I also cancel it by multiplying by 1/2. So what I've done is I've rewritten the original problem, multiplying 1/2 on the outside, 2 on the inside, and that gives me exactly what I need to set up my u substitution here. It's not the only way to do the problem. We could also divide both sides by 2 and obtain x minus 1 dx equals du over 2. They'll both accomplish the same thing here. And so my new integral then, written in terms of u, well, that x minus 1 times 2, that's 2x minus 2 dx. That just leaves me with a du on top, or 1 du, and then a u down below. And that's a pretty straightforward antiderivative. That will give me 1/2 times the natural log of absolute value u. And last step then is to rewrite it in terms of x. There's still my u steps in red there, so I switch code. So I'll go back and rewrite my final answer. It's 1/2 times the natural log of absolute value x squared minus 2x plus 5. And I should have a plus c here. And I should really have, to be 100% correct here, I should also have a c as soon as I've taken my antiderivative. So here's a u substitution problem. That's from section 6.2. I know that's one of the trickier topics for a lot of people in the chapter. And then remember, chapter 5 was just about derivatives of natural log and exponential functions, so you can expect to see some of those on the exam. Here is the antiderivative of an exponential function. I wouldn't be surprised if there's some students who can see what's going to work here, kind of guess and check it. I'm still going to use a u substitution here. I'm going to use a u substitution equal to our power there. So I'm going to let u equal negative 2x, and then du is just negative 2 dx. And now I'm almost where I need here. Since I showed it the other way in the last problem, I'm gonna show it the way I think that the book shows it, which is to say, all right, well, we have a 2 dx that we could substitute for. We don't exactly have that here. Instead of messing with the original problem, I'm going to mess with this substitution factor by multiplying both sides by -1. So negative du equals 2 dx. And now I can substitute into my problem. So my new problem written in terms of u is the indefinite integral of e to the u, right? That's my e to the u. And then the 2x is going to become a negative du. So that's a pretty easy antiderivative. Just negative e to the u plus c. And then my last step is to rewrite it back in terms of x. And that would be negative e to the negative 2x plus c. Quick reminder for any of these integration problems, you can and you should, because this is our final exam, you should check your answers. Check your answers by differentiating, right? If I end up with this as my final answer, I can take the derivative of my answer and see if it equals the original integrand here. It's definitely worth the time if you have I think 3 hours to complete the exam, so you should be able to check your answers here. Okay, so the next group of problems, there are 3 initial value problems. I think I'm just going to do one of them, but talk a little bit about what's going on. So what we have in this problem, this is the 3rd example among that group, is what we call a differential equation. This is a differential equation, so it's an equation that gives us a derivative, or that involves a derivative. If you think about what this is doing, it's not telling us what the function is, it's telling us how the function changes, right, by its derivative. And we're going to find the original function f. So a few things to think about. One, there are many different functions whose derivative is x squared minus 2x plus 3. In particular, any function of the form x cubed over 3 minus x squared plus 3x plus c is going to have this derivative. So our general strategy here is going to be to integrate f prime of x, right? We want to go from a derivative to the original function. And when we do that, here we have x cubed over 3 minus x squared plus 3x and plus c. Now this c is what makes this a family of functions. It's a whole bunch of cubic equations that are shifted up and down, right, in the coordinate plane depending on what that value of c is. Now of those infinitely many functions, there's only one that's going to fulfill this criteria here, that f of 1 equals 2. So what we're going to do then is solve for the constant c that makes this true. So what this is saying is, like, when we let x equal 1, y will equal 2. And so then let's take our entire function, which is equal to f of x, right? And we're going to set it equal to 2 and let x equal 1. So then 2 equals 1 cubed over 3 minus 1 squared plus 3 times 1 plus c. That's a 3. So I just let x equal 1 in all these places. And now we're going to solve for c to finish the problem. So let's see. I can subtract 3 from both sides, giving me negative 1 over here. And add 1 to both sides. So then we have 0 equals 1/3 plus c. And then subtract 1/3 from both sides. And we get c equals negative 1/3. Okay, so again, I'm almost there to full credit on the problem. Last thing I need to do now is just write my definition for the function. So f of x equals x cubed over 3 minus x squared plus 3x minus 1/3. And that should give us what we want here. Okay, so again, this is what we call an initial value problem. You're given a differential equation that is an equation for the derivative. We turn it into an equation for the function by integrating, or by taking the indefinite integral. The indefinite integral gives us this constant term, this generalized constant term, but we can use what's called the initial condition here to narrow it down from infinitely many functions to a single one by solving for c. Okay, so next there's some questions where we're asked to estimate the area under the curve y equals x squared from 1 to 4, sorry, from 0 to 4, using Riemann sum with 4 equal subintervals. So I've set that up here. Here's x equals 4, 3, 2, 1. And in the review packet, they ask us to do this 3 different ways. They ask us to do a left-hand sum, a right-hand sum, and a midpoint sum. I'm going to do the midpoint sum just because I think that's something that we haven't seen a whole lot of. You've probably done a decent number of left and right-hand Riemann sums. So all that means is that we're going to use an x value in the very middle of each one of these intervals. So I'm going to go, for example, just to show one of these rectangles, halfway between 1 and 2. I'm going to come up to the function and use the height of the function right there. So there's one of my midpoint rectangles. Here's another one, and we're going to use that 2.5 is our input there, and then 3.5. Come up, height, there we go. Okay, and then finally, our first midpoint would be something like that. And so graphically, this is what's going on. You don't need to draw this out, although I think a lot of people find it helpful to do so. The important thing here is that our Riemann sum is going to be 4 rectangles. The area of each rectangle is going to be the width. So let's see, the width of each one of these rectangles is 1. And then we can just add up our 4 heights. So we'll call this f of x instead of y, just to keep good notation here. So 1 is the width, that's our delta x. And then we'll have f of 1/2, right? That's our first midpoint. Add that to f of 3/2, right? That's 1.5. And add that to, come down here, f of 5/2. And add that to f of 7/2. Okay, so we can find those midpoints individually, or you can find the first one and then add delta x each time. It's nice that the rectangles width are 1, so really we're just going to add the function values of these 4 points. Okay, well, the function just takes the input and squares it, so my first height is 1/2 squared, so we have 1/4. And then 3/2 is 9/4. 5/2 squared is 25/4. And 7/2 squared is 49/4. And now I'll just add those together. So let's see, 1 and 49 is 50, plus 25 is 75, plus 9 is 84. So 84 over 4. That does simplify. We don't really need to on the exam, but 21 is our estimate for the area there. Very common problem I think I've seen on a lot of the exams in this course and in other calculus courses is to give like a 2-part problem. One part where we ask you to estimate area using a Riemann sum, and then one question where we ask you to calculate the exact area using the fundamental theorem of calculus. So I'll add that on. It's not part of the original problem, but let's find the actual area beneath the curve from 0 to 4. So that would just be the definite integral from 0 to 4 of x squared dx. And an interesting thing to think about with, again, just coming back to this dx question. So when we took these rectangles here, each one had width delta x, right? And delta x happened to be 1 when we used 4 rectangles here. Another way of thinking about dx is an infinitely thin piece of x, like the smallest infinitesimally small piece of x that we could form. So we really are making rectangles of height x squared and of width dx, and then adding up an infinite number of them when we calculate this definite integral. The first time we defined the definite integral, it was actually as the limit of a Riemann sum. A Riemann sum that had as many rectangles as we could fit. There's infinitely many rectangles within the interval here. So, okay, well, fundamental theorem of calculus makes this pretty easy. It gives us x cubed over 3. I'm going to evaluate that at 4 and 0. Okay, so let's see. 4 cubed, that's 64 over 3. Let's see, 63 over 3 would be 21. So this is 21 1/3, so 21.3 repeating. That's the actual area. And you can see there, our midpoint estimate is actually pretty close. Right? And that should make sense, because if you see the error in each one of these rectangles, the amount that's above the curve right here, so there's an area above the curve, that's error. And then we're missing some area over here, that's also error, but in the opposite direction. Those look like they should mostly cancel, maybe not for all the rectangles, like this last one here, there's a lot more under the curve missing. So maybe it makes sense why this is an underestimate, but it's a reasonable estimate of the actual area there. A word of caution, if you're asked to use a Riemann sum to approximate something, do not give the exact answer. Right? That's not what you're being asked to do. You're being asked to show that you can create and evaluate a Riemann sum to find area. It's fine if you want to do this to like see how close your answer is. If it says to approximate and you give the exact answer by using fundamental theorem of calculus, you'll only get minimal credit on that problem. Okay, so one topic that I don't know if we actually did this on the quiz. I know there's some web-assigned problems on it, so I definitely want to mention here is average value. Average value is one of the applications of integrals that we encounter in chapter 6. And average value is an interesting one. I know I've given this example a bunch of times of like driving to Missoula or driving somewhere, and my speed varies throughout the course of the trip. The idea is if I want to find my average speed, right, if I want to find my average speed, I could sum, or I could integrate my velocity over however much time it took me and then divide by time. That would give me my average speed. The formula for finding average value is pretty straightforward. So average value, here's how I remember it. It's integral over interval. Integral over interval. Right? So to find the average value, well, let me show graphically what this even means. So f of x equals 4 minus x squared. That's a downward opening parabola. It looks like this. And we're starting at -2 and we're going to 3. So it's as if we're counting up y values, and obviously there's infinitely many y values as we go, starting from -2 and ending at 3. Some of those values will be positive, some will be negative, and averaging them all together. Okay, so integral over interval, or equivalently 1 over b minus a times the definite integral from a to b of f of x dx. These say the same thing, right? 1 over b minus a is the interval, like the width of the interval here. And then here's the integral itself. So for this problem, we're going from -2 to 3. So here's our upper endpoint 3, lower endpoint -2. And so we have 1 over 3 minus -2. It's the width of the interval, times our definite integral from -2 to 3 of our function 4 minus x squared dx. Okay, so that's 1/5. And I'll evaluate my antiderivative now. So we have 4x minus x cubed over 3. That's going to be evaluated at 3 and -2. And so we'll get that 1/5 out. If we plug in 3, we have 12 minus 27 thirds, my upper endpoint. And then we're going to subtract. Be very careful with parentheses and minus signs here. Plugging in -2, we have -8 plus 8 thirds. And I'm going to do some combination of like terms here. So for example, we have a 12 minus -8, so that's 20. We have a -27 thirds minus 8 thirds, so -35 thirds. Oops, that should be a 5, not a 2. And by the way, you can leave your answer like this. You don't really need to spend a whole bunch of time combining like terms. It's nice to maybe take it one step past here, but rather than write this in terms of 15ths, I think I'm going to leave it here. I'm out of space, and that answer is just fine. Okay, so I guess to wrap this problem up, average value, it's really just a formula. Integral over interval, or equivalently 1 over b minus a times the definite integral from a to b of our function. Okay, so for the last problem I'm going to do in this session here, this is, I think it's like problem 14 on the other section. It's an optimization problem, and optimization was a topic that sort of spanned the 2 different exams here. So let me give you the setup for this problem. We have a guy constructing a cylindrical barrel with a capacity of 32 pi cubic feet. The cost per square foot of the material for the side of the barrel is half the cost for the top and the bottom. Okay, so let's see, what do we have there? The sides are half the price, or to write that a different way, so top and bottom are twice as expensive. we want to know what dimensions are going to minimize cost here. And we've seen some problems like this before. Oftentimes, you're actually given an actual number, like, okay, the top and the bottom cost this much, and the sides cost that much. I think the key in these optimization problems is first reading the problem and understanding what it is that we want to minimize. We don't necessarily want to minimize the material being used. We want to minimize the cost, right? And the cost is different for the top and the bottom. So if we want to minimize cost, really the first thing that we need to come up with is a cost function. Like, what is the cost of this going to be? Okay, well, if I just write this out using words, if I write like total cost, how are we going to do this? Total cost equals cost of the top plus the cost of the bottom plus the cost of the sides, right? It seems silly to write this out, but I've had students who have been really successful, like sort of thinking about it verbally even before mathematically. So okay, we got three different things. Oh, by the way, the top and the bottom are identical, right? So maybe we can just calculate that once. And if we can come up with a formula for these three things, then we can use first or second derivative test on it and find the minimum here. Okay, so the weird thing is that we don't know the cost. We just know it's twice as expensive to do the top and the bottom as it is to do the sides. So let's just create a parameter, and this isn't a variable. Let's let S be the cost per, what are our units here, per square foot of the sides. Okay, so we're going to invent that parameter there. It's a constant, right, to allow us to write an equation. So if S is the cost per square foot of the sides, well, let's see, how are we gonna build the sides? Well, the sides, if we unwrap that cylinder, it's gonna be a rectangle, right? We're gonna end up with like two circles, not to scale, the top and the bottom, and then a rectangle. And that rectangle, if we unrolled it, the height would be whatever h is, right? The height of the cylinder is h. And then the circumference of the cylinder is going to be how wide that is. So our cost of the top and the cost of the bottom, well, they're twice as expensive as the sides. So they're going to be $2 per square foot times pi r squared. That's the area of the top. And then the cost of the bottom is going to be the same, 2s times the area pi r squared. And now this rectangular piece, well, has cost s per square foot, and the area is h tall, and then 2 pi r, right? That's the circumference of the circle. So the rectangle has dimensions h by 2 pi r. Okay. So here's my cost model. I'll rewrite that and combine some like terms. So cost as a function of r and h equals, let's see, we have two of these, so we have 4s pi r squared. And then let's see what we have here. We have 2 pi r. You know what I'm going to do? Actually, I'm going to factor out. Maybe I won't do that. I'll just leave it the way it is now. So s times h times 2 pi r. Okay. A lot of things going on here. The challenging part right now is that cost is a function of two variables instead of just one. And so somehow we need to fix that. What I notice here, we've been given this constraint that the volume has to be exactly 32 pi cubic feet. We haven't used that yet. That's sort of a giveaway that we're going to have to use this information to make a substitution. And really what we want to do, I'm sorry, these are being added together. We want to get rid of one variable or the other. I have r squared, an r, and then I have an h. It's probably a good candidate for me to try and get rid of the variable h by substitution here. So if we have that pi r squared h, that's the volume equals 32 pi, well, we can solve this for h, right? So divide both sides by pi, divide both sides by r, and we have, by r squared, we have h equals 32 over r squared, right? So 32 over r squared can then take the place of h in our equation. And so now we have a cost model that's just a function of radius. So 4s pi r squared plus s. We have 32 over r squared, so 32 over r squared times 2 pi r. Okay. So let me do some simplifying here. I'm going to rewrite this. And I'm going to do some factoring. I'm going to factor out a pi. I'm going to factor out, let's see, what else can I factor out? An s, and maybe also a 4. So 4 pi s. Right, those are all just constants that I'm factoring out. And then what I'm left with is r squared plus, okay, well, we factored out a 4 from 32 times 2, so that would leave us with 16. And then we cancel a factor of r, so we have 16 over r. Okay, so here's our cost model. Now we've turned it into a min-max problem, right? We can think a little bit about what would be a reasonable domain. Really, r could vary from 0 all the way up to infinity. So we don't have endpoints of that we need to consider here. We're just looking for the local minimum in this function. So I'll take c prime of r. The reason I factored this out is when we differentiate, right, we have a constant multiple rule, so that like 4 pi s stays factored out. And then differentiating, we have 2r. This is 16 times r to the negative first, so that would be minus 16 r to the negative second power. Okay, and we'll set that equal to 0. Once we set it equal to 0, we could even get rid of this 4 pi s part. We can divide both sides by that. We just have 0 equals 2r minus 16 r to the negative second power. And to solve this, what we'll do is add 16 r to the negative second to both sides, and then multiply by r squared. So that gives us 16 equals 2 r cubed. Okay, so 2 steps there, so I'm running out of room. I added 16r squared to both sides, then I multiplied both sides by r squared. On the left, the r squared cancels with the r to the negative second, and on the right, the r squared multiplies by r to give us 2r cubed. Okay, well, we can solve that. Divide both sides by 2, we get r cubed equals 8. And so r equals 2 is our critical point. So the only thing left to do is to determine or to argue why that must be a local minimum. I think based on my problem here, I'm going to take the second derivative test. Just get rid of this over here. Second derivative test says, let's take c double prime of r. So c double prime of r has this 4 pi s, which, by the way, is a positive number. That's important. Pi is positive. The cost for the sides is positive, times our derivative, so times 2. And then when we differentiate again, that minus 2 comes out in front, so we have 2 plus 32. I can talk at the same time. 2 plus 32 r to the negative third. And what's important here is if we're plugging in a positive value for r, that r to the negative third, that's 1/8. We're still getting a positive number plus a positive number times a positive number. So this whole c double prime of 2 has to be greater than 0. That means we have a concave up function. And by the second derivative test, a minimum then occurs at r equals 2. Okay, so we've now found one of our 2 dimensions. We've found that the radius should be 2 feet. And all that's left now is to find the height to finish the problem. If pi r squared h equals 32 pi, letting r equal 2 gives us 4 pi equals 32 pi, divide both sides by 4 pi, and we get that h equals 8. So that's our last step there, is to use our original equation for the volume to solve for our last parameter. So what we found is that the cylinder of radius 2 and height 8 is going to be the size that minimizes the cost. And I don't believe they've asked us to actually find, no, we can't find the cost because we don't actually know how much these materials cost. One interesting thing in the problem here, I created this parameter S to stand in for the cost of the side per square foot. In the end, it didn't really matter. Like, my answer didn't depend on S. That should make sense. Like, whatever dimensions are going to minimize costs are going to minimize costs whether the materials are $10 per square foot or $100 per square foot. What's important is just that ratio between the costs here. And that showed up in a couple places, right? So I did, I kind of like wrote this in the middle here, but the cost of the top is right here. Right? There's our top, and here's our bottom. And they each had cost 2s per square foot, and the cost of my sides just had 1s per square foot. So if you run into an optimization problem like this where they haven't explicitly given you the price, they've just given you like a ratio of prices, my advice here is to create your own representation of the cost. One other thing that I see students do sometimes, if they haven't given you the cost, you can invent the cost. You can say, for example, like, okay, well, I'm going to make the sides cost exactly $1 per square foot. And then the cost of the top and the bottom are exactly $2 per square foot. If you do that, you end up with a very similar equation just with no s's in it. So that's another way to do this that I've seen people do. Some people prefer to do it that way. Okay, guys, so just some advice before you start on the exam. You have 3 hours to complete the exam, so make sure that you're prepared before you start. Make sure that you start before 9 p.m. on Friday so that you have enough time to complete it. It's written to take about an hour or maybe less, it depends. But I want to make sure that people aren't rushed. We do have a time constraint just for academic honesty considerations. In general, some reminders, all your indefinite integrals, make sure that you use correct notation. So make sure you're writing that the integral symbol until, and the dx or the dt or whatever, until you've taken an antiderivative. Once you've taken the antiderivative, we should not see any integral signs. You should switch to an evaluation bar. For indefinite integrals, make sure that you have the plus c. Make sure that when you in your work that you show that things are actually equal, that you link them with equal signs. Change all those roots to fractional powers. Be really clear with your u substitution. If you're doing a complicated antiderivative and you use u substitution, write out u equals such and such, du equals such and such to show your steps there. Other than that, I guess just reminders that the chapter 8 topics are not on the exam. Our quiz due this evening has those topics covered, so you don't have to worry about that. And the emphasis is very much on integration. There's a few problems involving applications of differentiation. I think maybe just last comment from what I've seen on quizzes and our first exam, there is a problem, or at least one problem where you're asked to interpret in the context of the problem what your answer means. Anytime you're asked that, bring it back to the original context. So for example, we had, I think earlier in the semester, we had a problem about fish. And there's a growth function that talks about how large fish grow over time. And you're asked to interpret the limit of that function as x approaches infinity. Don't use the language of calculus. You're supposed to be speaking not to your calculus instructor, but to someone who doesn't know calculus. So if the problem's about fish, explain what the derivative or the limit means in terms of fish and time. If you're asked to like interpret f prime of x, for example, it's not sufficient to just say like, oh, well, f prime of x is the derivative of f, or it's the instantaneous rate of change in f with respect to x. Really tie it back to whatever the context of the problem is, like whatever it is we're talking about in real life. I hope the exam goes smoothly. If you run into any issues during the exam, feel free to email me. If that happens, If you have some sort of glitch, whatever, do as much work as you can. Be sure to save all your problems just because you're working under a time constraint, and let me know and I'll take a look at that. I'm also available between now and also during the day tomorrow if people want to conference individually. As a final reminder, really appreciate it if you fill out the course evaluations, especially as we're moving more things online. It's really helpful to know what sorts of things worked and didn't work, or that we can improve on. And if we get a sufficient response rate, and again, I can't read these until after the course, but if we get enough people who respond, 80% of the active students, I'll drop a second quiz grade from your average. So if this is the last time I see you on video, thank you for a great course. From my perspective, I really admire the hard work that you guys put in. It's hard learning calculus on your own. I appreciate your diligence on the assignments and all the communication I've got from folks joining the live sessions and tuning in remotely. I know you guys juggle a lot of things to make this course happen during the summers, that you have work and all sorts of other things. I'm really looking forward to seeing people back on campus in the fall and doing some in-person teaching. Feel free to come up to me if you recognize me and say, hey, I was one of those virtual students that you never saw, but that communicated with over the course of the summer here. Okay, so wish you well, good luck on the exam, do good math, show your work, see ya.